Welcome to Taylor polynomials. So recall in the previous video, right? So in the video section 8.6, part 4, when we were solving our differential equation, so when we were solving our differential equation for a solution, P of t equals a sum from n equals 0 to infinity of a sub n times t to the n. We found that our a sub n's had to equal the nth derivative of p evaluated at 0 divided by n factorial. And this particular formula didn't depend on the differential equation at all. Right? And this formula didn't depend on the differential equation. We used the differential equation to figure out what the nth derivative of p at 0 was, right? So we used the differential equation to find that nth derivative of 0, evaluated at 0, right? So this particular formula seems to be pretty inherent to power series. And in fact, we can sort of create a try to create power series, or at least polynomials, to approximate a function in this same manner. So I'm going to do the definition in just a moment. So essentially, if we start with a function instead of a series, then we can come up with polynomials to approximate our function. So we can come up with the polynomials to approximate our function. Using this formula for the coefficients. So this will be kind of the basis behind what we're doing here. So definition. if we have a function f whose derivatives exist up through at least the nth derivative. So if we have a function f, which is differentiable, near x equals c, then the nth degree Taylor polynomial approximation of f at x equals c is the polynomial p sub n of x is equal to the sum from k equals 0 to n of the kth derivative of f evaluated at c divided by k factorial times x minus c to the k. So essentially what we have here, I have generalized this or translated. So instead of just focusing at 0, we can now shift by c, right? And so all that has changed is instead of plugging in 0, we now plug in c to our formula for the coefficients. We also have a Maclaurin polynomial. The Maclaurin polynomial, c is equal to 0. So the nth degree Maclaurin polynomial is the Taylor polynomial with x equals c. So is the Taylor polynomial at, with c equals 0. So it's the Taylor polynomial at x equals 0. So for example, let's find the nth polynomial for f of x equals e to the x. And then we'll take a look at how the polynomials p1 through p6 become better and better approximations for e to the x. So f of x equals e to the x. Oh, I should have said the nth Maclaurin polynomial. Okay, so f of x equals e to the x. This function's easy to work with. We know that the nth derivative of e to the x is also e to the x. We are looking for the Maclaurin polynomial. So the Maclaurin polynomial we have that Pn of x is equal to the sum from k equals 0 to n of, we take the kth derivative evaluated at 0 divide by k factorial, and then we just have times x to the k. So our kth derivative evaluated at 0 is just e to the 0th, or 1. And so this time we get that our polynomial is the sum from k equals 0 to n of 1 over k factorial times x to the k. Or in other words, nth degree polynomial is just, we would have 1 when we plug in k equals 0. We'd have 1 over 1 factorial for k equals 1. So 1 over 1 factorial times x. Then 1 over 2, add 1 over 2 factorial times x squared. Plus 1 over 3 factorial times x cubed. And we would go all the way up to 1 over n factorial times x to the nth. I'm actually going to eliminate the x cubed term just so I have more room. So we go up to 1 over n factorial times x to the nth. This is our nth polynomial, Maclaurin polynomial approximation for e to the x. So if we have the p0 is just 1. p1 would be 1 plus x. p2 would be 1 plus x plus 1/2 x squared. p3, we would have 1 plus x plus 1/2 x squared plus 1/6 x cubed, etc. Right? So if I switch over to Desmos, we can see kind of what these various approximations look like. So if we switch over to Desmos, I have here the graph in blue is e to the x, and then that black line is p1. So I'm going to just take a picture of this, and so I can put them in my notes. Then if we change our capital N on the left to 2, it's now calculating p2. So I have the sum notation on the left. I wound up using capital N's for my degree of the polynomial, lowercase n's for my index. We could certainly change this so that it's matches what's in the notes and put k's. But here is my degree 2 polynomial and how it corresponds to e to the x. So note, very close to x equals 0, that quadratic is actually pretty similar to the exponential function. Right? So let's take a picture to put in the notes. Now let's change this to cubic. So here, it extends a little further where the cubic function looks very similar to e to the x. Then we can make that the degree 4 polynomial. And now look how close the function is all the way up to x equals, say, 2. On the right, e to the x looks very similar to that degree 4 Maclaurin polynomial. And it's actually, we get pretty close to -2 on the left, up to about -1 or down to about -1.5. The functions look very similar. Now we can do our degree 5 polynomial. Here we can go almost all the way down to -2 on the left, and we go well past x equals 2 on the right for the two functions looking very similar. If we do another one, let's look at that degree 6 polynomial. Again, we're getting closer and closer and closer to the polynomial matching our function. And we can actually go pretty far out to have the polynomial look very similar to e to the x. So on the left, we're now below -2. On the right, I can go pretty far and have the two functions very, very close together. So that's getting more like to 4, where the two functions are very, very similar. So you can see here again, we have a pretty low degree Maclaurin polynomial that looks very, very close to e to the x, at least when we're sort of within 2 of 0, right? Between -2 and 2. So I'm going to go ahead and just transfer those over to our notes. Oops. So if we go over to our notes, we had here was P1. And so this was P1 versus F. It was not particularly close once we got very far from x equals 0. Then if we look at our P2, and we have our P2 and e to the x, or f, and they're looking pretty close, from about -0.5 to 0.5. And we could keep going. I will add the rest of the pictures on my own time to the notes, so you don't have to watch me doing this in the video.